next talk's going to be, this is not the title slide, but I think it's going to be on Sculpting Quantum Speedups by Scott Aronson and Shalev Ben-David, and Shalev's going to be giving the talk.
Okay, thanks. So, yeah, I know this is the last talk before the free afternoon, so thanks for going. Yeah, I know life is short, and given recent political events, it might be very short. So, you know, just one more talk, and then we get to enjoy Seattle's attractions, which presumably include walking around in the rain, sipping Starbucks coffee, I assume. Okay, so my talk is about sculpting quantum speedups, which is basically a query complexity result. In query complexity, we have a Boolean function f, and we're given access to, we can oracle access to a string x, and we want to compute f of x. So basically, we get to query the bits of x. The cost is the number of bits we query, the number of queries we make, and the goal is to compute f of x. So for example, if f is OR, then an algorithm can look something like this. Here's the input, and these are all boxes that are sealed. And then we can say, OK, what is in this box? We see a 0. What is in that box? And so on. If we see a 1, we know that the OR of all the bits is 1. So now we can stop. So this took us 3 queries in this case. Right? And the query complexity of f is the worst case number of queries we would need to make. The worst case number of queries we need to make. So we will denote it by d of f for deterministic algorithms, r0 of f for zero randomized, and we also have bounded error randomized algorithms, quantum algorithms. So these are all query measures that we can define based on basically what kind of algorithms we are considering for computing f from the input string. And of course, we have quantum queries faster than randomized, faster than deterministic. OK, so so let's just summarize a bit of previous known results. We have, I guess, one of the fundamental results is the Beals et al. Result from '98, which says all of the query measures I defined on the last slide are polynomially related to each other for total functions f. So this means just for normal functions f. All of these measures are the same up to polynomial factors. So in last year's QIP, there was this excellent result by Ambianis et al. And they basically just give some surprising polynomial separations between those same measures. So this tells us they're all polynomially related, but they're not all exactly the same. They're polynomial separations. And we also had a result in last QIP, which is basically even more quibbling over polynomial factors, right? And so, you know, at this point, you'd probably want to say, well, you know, enough polynomial factors. Real complexity theorists don't care about polynomial factors. Where are the exponential speedups, right? So can we get exponential quantum speedups, for example, in query complexity? Well, we know you can't for total functions. But we also sort of know that you can. So what is the catch? Exponential quantum speedups are possible if there's a promise on the input. So if we know that the input string, we are guaranteed in advance that it will have some extra structure, then you can get exponential speedups using a quantum query algorithm versus a classical query algorithm. So for example, the promise might be the input string has some periodicity. OK. So this is the basic story of query complexity. Here, for this talk, we want to ask, you know, when are these exponential quantum speedups possible, right? So we know they're sometimes possible if you have the right promise in the input, okay? But for what types of functions? So again, for total functions, we're not going to get anything. If there's a promise, maybe. Okay, but for what kinds of functions, what kind of promises, can we say anything else about when we get exponential quantum speedups? In particular, we're going to ask the following question. Given a total function f, is there a promise that we can put on f such that we'll get exponential quantum speedups once we add in this promise. Okay, so this is a property of f. It's either possible or not possible to add in a promise and get an exponential speedup. And we're going to call this is what we're going to call the sculpting problem. Okay, so again, the sculpting question is, given a total function f, is there a promise such that there are exponential quantum speedups after we add in the promise? In other words, let's more colloquially, we're going to say, we know there's probably no exponential quantum speedup for 3-sat because it's NP complete, but maybe on some special set of instances of 3-sat, right? Maybe there. We want to say basically we want a press headline that looks like this. There's an exponential quantum speedup for 3-sat with a little star that says, well, if you restrict to a sufficiently artificial set of 3-sat inputs. Okay. So our result basically characterizes, at least in query complexity, when this is possible. For what functions you can restrict them to a promise to get exponential speedups. Okay. So let's just go with a quick example here. The example is the OR function we had at the beginning. Can we restrict the OR function to a promise such that on inputs from that promise, there's an exponential quantum speedup? Okay, so let's just think about this for a second. So again, the inputs are just these n boxes, right? And we want to, if we put in a strong enough promise, it will be easy to solve the OR function. Maybe I promise you the boxes are either all 0 or all 1, right? If I promise that, then just open one box. That's enough, right? But that won't give you a gap between randomized and quantum algorithms. That will just make them both small, right? So can you come up with a promise that makes the quantum algorithm fast, but the randomized algorithm still slow? Right? What do you guys think? OK, so I mean, for the OR function, the answer is no, which is maybe intuitive. This is a result of Aronson from 2004. So actually, the speedup is exactly quadratic. So that's kind of neat. No matter what promise you put, quantum algorithms will be quadratically faster than the randomized algorithms. OK, so let's try a different example. What about the parity function? So now we want the parity of the bits in the boxes. Can we restrict that to a promise such that now it's easy for quantum algorithms, but still hard classically? OK, so the answer is actually yes. There's a trick you can do, which looks something like this. Let's split the input into 2 parts. Now, we want the parity of all the boxes, right? But we'll cut it up here. And over here, we'll add in the promise that this part of the input satisfies the promise for Simon's problem, which is just a problem that we know you can do exponentially faster with quantum algorithms. So over here, we'll just say this part of the input satisfies that promise. And over here, we'll just put in some string such that the total parity of this whole string will be the value of Simon's problem on this string. So this part will just be whatever it needs to be to turn the problem truly into Simon's problem. Okay? So now a quantum algorithm can just look here. It doesn't even need to look at the rest and solve Simon's problem in like polylog n. But a classical randomized algorithm, well, it can't look here because then it's trying to solve Simon's problem. Over here, there's no structure. It's just a parity. So you can show that this works, that the classical algorithm will have nothing that it can do. So it will need exponentially more than the quantum algorithm. OK, so now our result is a characterization. So before I tell you what it is, maybe you can try to guess what's the difference between an OR and a parity, right? What will the characterization be, right? What property puts OR on one side and says this is not sculptable, and puts parity on the other side and says this is sculptable? OK. All right, so let me go on a bit of a tangent before I tell you the answer, and this is going to be relevant eventually. We'll talk about H indices. Do you guys know what an H index is? It's used to measure research output. It's like the maximum number k, such that you have at least k publications with at least k citations each. This is your h-index. And actually, we're going to consider a variant that I think is better, and everybody should switch to it. It goes, the maximum number k, such that you have at least 2 to the k publications with at least k citations each. Okay? So this is what we're going to call the h-index in this talk, this 2 to the k variant. So if you go to your Google Scholar page, it probably looks something like this. You have your list of publications, and over there in the corner, you see the h-index, right? And Erdős' h-index is, can you read this? I think it says 108. And there's also an h-index since 2011. I assume they mean citations since 2011 rather than publications. So that would be truly impressive. OK. So, all right. So here's what we're going to do. We're going to look at the citation at the Google Scholar page for the OR function. It's going to look something like this. This is actually, you got the wrong picture here. This is an add function. OK. All right. So we're going to look at, this is the Google Scholar page. The publications are going to be the inputs. So inputs, we're going to call them publications. There's always 2 to the n of them, right? Because there are 2 to the n strings, Boolean strings on n of size of length n. OK, and the citations are going to be something called the certificate complexity of the input. So here we have the inputs. Here we have the value of the input. So like this is a 0, or of this string is 0, or of this string is 1. Right? So there's only one 0 value. Everything else is 1. And in the third column here, we're going to have the certificate complexity of the input. What is the certificate complexity? It's the number of bits I would have to show you to convince you that this input truly has this value, that this value is correct. Right? So for this input, I have to show you all of the bits to prove to you that it's a 0 input. But for every other input, I can just show you the 1 wherever it is, and that will convince you that OR of this set of strings is 1. Right? So the certificate, we're going to call those the citations. So here, OR has one input with very good citation, with n citation, right? The n certificate complexity. Every other input has 1. So the h-index for OR is 1. OK. OK, but what about for parity? So this is the Google Scholar page for parity. Again, the same number of publications, 2 to the n. It's always 2 to the n. But now, the certificate complexity is n for every input. So every input, I need to show you all the bits before you're convinced of its parity. OK, so this is just n everywhere, and the h-index will be n. Right? There's 2 to the n publications with n citations each. OK, so we're going to claim that the h-index, as defined like this, actually characterizes sculptability. Basically, this is the h-index of the certificate complexity of the function. And we're going to say that sculpting, well, we're going to prove that sculpting is possible if and only if the h-index of the certificate complexity of the function is large. So for OR, it was 1, so sculpting is not possible. For parity, it's n, so sculpting is possible. Formally, the statement looks like this, basically. So we can try to parse this. It's saying for every function f, whichever function you give me, there will be a promise that you can restrict to, such that the randomized algorithm takes at least the h-index of f to the power 1/6 divided by some logs. OK? So the randomized algorithm will take time polynomial in the h-index. But the quantum algorithm will take time logarithmic in the h-index. OK? So if the h-index is large, this is an exponential separation. OK? The second statement is sort of the other direction. And it's saying, for every function, no matter what promise you try to restrict to, the randomized and quantum query complexities of f restricted to the promise will be polynomially related, but there'll be a factor of the h-index there. So if the h-index is small, this is a true polynomial relationship. But if the h-index is like large, is like n, then this gives you nothing. OK? So together, these results say the h-index is really what you care about. If it's large, you can sculpt. If it's small, you cannot. OK, so this is the main result. We also have a few other results. You can ask sculpting not for randomized versus quantum. You can just take any of these other query complexity measures and ask the same question there. So here you can ask D versus R0, the deterministic versus zero error randomized. Actually, it's the same characterization. So the H index comes up again, and it's just the same characterization. OK. What about R0 versus R? So zero error versus bounded error. Here, it turns out it's always possible to sculpt. And the rough intuition here is just, again, the OR function. Think of the OR function. Think about trying to restrict it to a promise such that under this promise, you can solve it faster with a zero error randomized versus deterministic. If you think about this, you'll realize this is not possible. These are always going to be the same, the zero error for the OR function. But on the other hand, for bounded error, you do get an advantage for computing OR if you restrict to the right promise. Right? Why is that? Because, you guys see it? I can restrict to the promise that says the Hamming weight of my string is either 0 or n over 2. Right? And now, if I want to make sure I didn't make any errors, I still sort of, so suppose I query and I keep seeing zeros. Right? So I can be pretty sure it's the 0 input and not the half ones input if I query randomly and keep seeing zeros. But if I want to be completely sure, I'm going to make like n queries. Right? If I am OK with bounded error, then I can just solve it in constant queries. In constant queries, I'll see no ones. I'll know that the input is probably the 0 input. OK. All right. So I guess there's a bit of some philosophical questions here. Why the H index came up? Why certificates? Let's answer this one first. Why certificates? How is that related to the sculpting question? The answer is it sort of is not, because actually the H index of certificate complexity is polynomially related to the H index of block sensitivity and the H index of a bunch of other measures you could have put there. So really, when we say characterize by the H index of certificate complexity, well, up to polynomial factors, which we lose anyway, it's the same as the H index of block sensitivity or of other measures. So really, this H index is up to polynomial factors, something fundamental, but the certificates are not that fundamental here. OK. Right. So intuitively, what is the H index doing here? It's saying, is the number of hard inputs, the inputs say that are hard to certify, is that number small or large? Right? If the H index is large, it's saying almost every input or many inputs are hard, not just one input is hard. If the H index is small, like for OR, it's saying there's really only one spot where the function is hard. Really, around the 0 input for OR, the function is hard. Elsewhere, it's not hard. So if the function is hard everywhere, you have more room to sculpt. You're starting with a larger sculpting block. If the function is only hard in one spot, you have less room to sculpt. So in fact, you cannot. So this is the intuitive argument here. OK, so let's quickly go through just one slide on a proof sketch for the impossibility direction. So how do you show that, for example, OR cannot be sculpted? Right? We want to show that randomized algorithm and quantum algorithms are polynomially related as long as you add in this H index term. Right. So basically, we're saying if there's few large certificates, R and Q are quadratically related. This is what we want to show. So the argument looks roughly like this. It says, OK, step 1, we're going to use this standard argument of that deterministic algorithms are at most the square of certificate complexity. If you don't know it, that's OK. But this is a standard argument in query complexity. And we'll just apply it here, and it will sort of try to kill the small certificates. Because we know D is large to begin with, we'll try to apply this argument to remove small certificates. If we do this, we'll have few 1 inputs left. And the step 2 will be show the quadratic relationship when your function has few 1 inputs, when your function on your promise has few 1 inputs left. then we will just show that there's a quadratic relationship whenever that happens. Okay? And this is what we do. And we get, along the way, this nice side result. It basically says, actually, quantum query complexity for any function, even a partial function, is quadratically related in at least root of the deterministic query complexity, but divided by the log of the domain size of your function. Right? So you can view this as a tool for lower bounding quantum query complexity if you want. Right? This tool says, OK, suppose I want a lower bound quantum query complexity of the OR function. I want to show it's like root n. Okay? So first, I'll just restrict to the promise where the input is either the all zero string or it has Hamming weight 1. So now I've restricted to a set of size n plus 1, only n plus 1 strings left. And I'll show that even on this set, the quantum query complexity is large. Okay? So how will I show this? Well, the deterministic query complexity is clearly large. That's not hard to show, because you'll just deterministic query, you'll keep seeing 0. So the deterministic query complexity is n. And then you plug into this result, and you get root n divided by log n plus 1 is, up to constant factors, a lower bound on the quantum query complexity. Okay? That's it. So you get the Grover lower bound with the log factor loss. But you didn't have to do any work. You just plug this in, basically. So on the scale of quantum query lower bound techniques, this is a pretty weak technique, but it's a very easy to use technique. So it's a trade-off between like easy to use and the strength of the technique. Okay. I had this on the slide. Okay. The proof idea for proving this is basically if you know what this randomized certificate versus quantum certificate result of Aronson from 2004. This is basically generalizing that, I would say, is the key part of the proof technique. Okay. So I'll briefly sketch the sculpting existence result. That's the other direction. Why parity is possible to sculpt. I mean, we saw it for parity, but why is it always possible if the H index is large? So here, we want to find a promise that has a certain property, right? That leaves the classical query complexity large, but makes the quantum query complexity small. Basically saying if there are many hard inputs, we can find a promise on which is an exponential separation. So the step one will be we actually don't want to use certificates. We want to use the block sensitivity thing I was talking about before. Step two is something called Sauer's lemma. I'll briefly talk about Sauer's lemma. And step three will be using a communication complexity result. So let's just very quickly look at that. Sauer's lemma is this kind of cool technique about sets of Boolean strings. It's a cool result about sets of Boolean strings that is very good to know. It's saying if you have a set of Boolean strings, like here we have these 5 strings, then you can, if it's a large set, you can always find a set of positions, like these 2 positions, bits basically of these strings, where on those bits you have every possible action. So on those bits you have every possible string. On those bits you have 0, 0 here, 1, 1, 0, 1, 1, 0. Okay, so on those bits you have every possible action. Okay, and you have a guarantee on the size of the set. The size of the set would be log s divided by log n, at least. Okay, so it's always, if s is like 2 to the n, or s is 2 to the poly n or something, you will always have a largish set of positions where you have every string if you just restrict to those positions. Okay, so this is basically saying we know that we're in a function that has a large h index. So basically, there are many hard inputs, right? There are many hard inputs. We use Sauer's lemma, and we can say the hard inputs basically look like this. Over in these bits, you have every possible action. Over in these bits, well, we don't know what happens, right? It can be anything, not every possible action, right? Let's call it some function of the x here. So here you have every possible action. Here you have some function of x. That's what all the hard inputs we can assume have this structure. And by Sauer's lemma, this x part won't be too small. Okay. So, OK. Right. So now we want to define a promise. We want to restrict this set of hard strings to a promise such that quantum algorithms can solve it fast and randomized algorithms cannot. So what we'll do is we'll just put the promise on the X part. We'll say, well, here we started with every possible string. Right? Let's just put Simon's promise there. Right? And the problem is, OK, you don't just get access to the X part. You get access to the whole string. So you could worry, maybe this says Simon's problem, but here, this S of X tells you the solution to Simon's problem just in the third bit. So the even a deterministic algorithm can solve Simon's problem by looking at the third bit, because maybe this string just tells you the solution. In fact, maybe this S of X parts contains the answer to every possible function that can be solved in logarithmic time with a quantum algorithm. Right? So maybe not just for Simon's, but for every function where you have a quantum speedup, the S part will tell you the answer. Can that happen? And this is where our reduction to communication comes in. Basically, we take a communication task where you have a quantum speedup. So communication task has an X and a Y, right? So the X will be identified with this X. We'll give that to one of the players in the communication game, to Bob. And then we'll consider giving strings Y to Alice that satisfy the promise of the communication problem. And now we consider Alice strategies that look like this, classical strategies that look like this. Alice knows Y. She wants to find out, basically, the joint function of X and Y. She asks questions either about X or about S of X. She asks questions basically from this string. She basically queries this string by asking Bob questions. Okay? She does this, and she tries to, using a classical algorithm, solve the communication task that we said she cannot solve, because we know we picked the communication task to be hard to solve classically. Okay? So this is the situation. She's going to try to solve the communication task that she's not supposed to be able to solve by asking Bob questions from X or S of X, basically by querying this string. We know that will fail. Okay? What does it mean that it will fail? It will mean that basically there is some input Y for which Alice cannot do this with few queries. There exists a Y such that Alice cannot solve the communication game with this strategy quickly. Okay? Now we'll fix this Y. All right? If we fix a Y in a communication problem and we look at possibilities for X, we really get a query problem. We get a function of X. We get a function of X, right, where f of X is the communication game of XY after we fix the Y. So that is going to be the function that we will put here for X. Okay, so we will restrict X to the promise. We will place on X here the function that you get from this communication problem after we fixed Y to make this problem hard. And then we can show that there's no query strategy the classical query strategy that does this quickly. Okay, so probably hard to follow that. Let me just, in 2 minutes, talk about sculpting in the Turing machine model. So in the Turing machine model, so there's no longer query complexity. In the Turing machine model, we can ask sort of a similar question. We can say a language is sculptable if you can restrict it to a promise such that now it's in promise BQP but not in promise BPP. It can solve by quantum algorithms but not by classical algorithms. Okay, so to be sculptable at all, we must start with a language that's hard. We start with a language outside of BPP. It turns out that if a language is something called paddable, you can add irrelevant chunks to any input. Like 3SAT has this property. It turns out that for those languages, we can show sculptability assuming a complexity theoretic conjecture that promise BQP is hard on average for P/poly. Okay. And we have another result that says, actually, every language can be sculpted in the Turing machine model if you assume a stronger conjecture, which says that there is a BPP bi-immune language for BQP. Okay. doesn't matter exactly what that is. But if you assume sufficiently strong conjectures, you get sufficiently strong result. You get equally strong results. OK. So just to conclude, we gave a full characterization of sculpting in the query model. We wanted to say something like this, right? We wanted to say quantum computers give an exponential speedup for some 3-stat instances. This is now complexity theorist approved, or at least I'm going to say it is. Scott's not here. Don't tell him I said this. OK, actually, no, this is fine. It's just the word sum here is doing a lot of work, right? The sum is going to be particularly artificial 3-stat instances, not any ones that come up naturally. OK, and then we showed most Boolean functions are sculptable. So one thing we can conclude, or one conclusion I draw from this work, is that quantum speedups are fundamentally not about the function so much as they are about the promise. The promise tells you a lot of information about whether you're going to have a quantum speedup. The function tells you, even parity can be restricted to a promise. So, the function doesn't tell you that much about whether you're going to get a quantum speedup. Certainly not as much as the promise. And, for future work, I think, I sort of want to push this question. As a community, we should address which promises give rise to quantum speedups. For which promises can you find a function where you have exponential quantum speedup? Can we characterize those? It seems like a much harder task. OK, thanks.
All right, we have time for questions. Over there.
Wait. If given the oracle f, can we compute the h index in the polynomial time?
Right. So the h index. OK. So the h index is a reasonably simple measure. So if you give me the truth table of the function as input, so that's an exponentially long input in n, right? Because it's the truth table of the function. Yeah, then I think so. I wonder, the way you stated that, maybe the answer is no, but just because you can't sort of tell anything about the function in polynomial time if you want to be polynomial in n. So you've got to be a bit careful here. But basically, the h index is simple enough that, for any function you give me, I can quickly tell you what the h index is. We can compute it for parity. We can compute it for majority, for and/or trees, for whatever you want. So I think, at least from a what we can prove about it point of view, it's a simple enough characterization.
More questions?
When constructing an oracle, you often have a situation where there's some complicated arbitrary function, and then you reduce it to a true-false by some method, like saying, is the output of my complicated function inside of the following set, or does the output of the complicated function have an answer less than or equal to some constant? Generally speaking, if you could come up with some promise that used the characteristics of the pre-existing complicated function as it moves toward the oracle function, that would be very helpful. Do you have any ideas about what techniques exactly would allow us to sculpt these kind of functions to produce the exponential speedup?
OK, so the sculpting results here, which basically says that most functions are sculptable, or in the Turing machine model, maybe even all functions are sculptable, or all languages. So those are very strong results, and they're really cheating, right? Because they're really restricting to a particularly artificial set that turns your function into a completely different function. You're finding inside your problem, well, you're not finding Simons exactly. You're finding this instance of the communication task, but you can think of it as finding Simons somewhere hidden in your function. So, from that perspective, I think this result doesn't have that much application of the sort that you're hoping for, like of the sort that maybe you can sculpt in some natural way. I think sculpting in a natural way will be dependent on the exact functions you're looking for. So that there's some work by on and/or trees by who is this? I think Stacy Jeffrey and Shelby Kimmel and maybe someone else, where they basically essentially show maybe a more natural sculpting for how to sculpt specifically one function, the and/or tree. So for one specific function, they work hard and they show a sort of more natural sculpting effectively. Right? So using this, you can say, okay, well, all functions are sculptable, but in a very ugly way. So if you want a natural sculpting, I think it will be much more difficult.
Any more questions? There's a question over here.
So I think to get this result, you used an exponential gap between classical and quantum in communication complexity.
Right.
I was wondering if you can use this gap to prove another gap in somewhere else.
Sorry?
Like you used the exponential gap in communication complexity to get an exponential gap in query complexity.
Mm-hmm.
I was wondering if you can do something similar using the exponential gap in query complexity.
Yeah, I'm not sure. I mean, I guess exponential, since communication complexity is sort of so much hard to prove things about, there's a natural expectation that once you manage to prove it, it will be a very useful result. And here we indeed see it has all these applications. The query complexity results, I would say, are somewhat easier to prove. So you maybe expect to have somewhat less applications. But so, for example, this particular query result, I don't know what its other applications are. I could actually. So one quick point is that cheat sheets talked about in the last QFP have this flavor a bit, where you take a partial function separation and you turn it into a total function separation in query complexity. So that's a query complexity to query complexity reduction of speedups. Maybe that's what you're looking for.
Any more questions? Nope. All right. If not, let's thank the speaker again.